Text and web search 2, ranking and crawling. One of the classical contributions of traditional information retrieval is the idea that we want to rank the results. And this came up in the Salton work at Cornell in the 70s. And the basic idea was to treat documents in what's called a vector space model. So you have to think a little bit abstractly to get this, but it makes perfect sense once you do. Think of every document as a vector. And by this I mean, imagine that you have a dictionary of 10,000 possible terms. Then each document being a bag of word means we can represent it as an array of 10,000 counts, where the first element in the array is the smallest word in the dictionary, the second element in the array is the next word in the dictionary, and so on, up till the last word in the dictionary. For every word in the dictionary, we put in a count of the times that word occurs in the document. Obviously, this vector will be almost all zeros for every document, with non-zero entries for the words that occur in the document. And if you think of the world this way, then every document is a point in 10,000 dimension space, which is a little hard to visualize, but in the upper right here, I have a very simple three-dimensional space with three terms, Justin, Bieber, and database. And we can see that three different documents might be at three different points in this space based on how often they have the terms database, or Justin, or Bieber. Okay? Now, documents can be thought of as vectors. Queries can be thought of as documents or vectors also. A query is just a set of words, and we can rank all documents by its distance to the query document. So if you think of your query as a point in 10,000 dimension space, maybe what you're looking for is all the documents that are close to your query document. Many problems in artificial intelligence can be mapped down to these kind of vector space near neighbor problems. We're trying to find neighbors of a point in a vector space. And obviously the trick is to convert your objects into a vector space where near neighbors are relevant. Okay? So choosing your vector embedding or your vector space model is extremely important. The vector space model I just gave you for information retrieval is not sufficient, and we'll see that in a minute. We're going to need to tune it up to make it make sense. So a standard way to get a better vector space embedding in information retrieval is what's called the cosine similarity distance metric. It stems from the following problem. Two long documents in our naive metric, so the naive metric is where the vector contains entries that are just the counts of each term occurrence. Two long documents will be further away from the origin than short documents. And this may make long documents appear more similar to each other than they are to short documents. Even though the short documents might be looking for long documents, the short documents might be queries, and the long documents might be potential answers. And so what we want to do is we want to get those long documents down at the sort of similar distance from the origin as the short documents so that we can sort of measure them on a common ground. And the way we'll do this is we'll normalize each document's vector, we'll normalize each dimension in each document's vector by the vector length. So we take each dimension in the vector, we divide it by the total length of the vector. Once we've done that, every document now is exactly one away from the origin. And so all the documents sit on the outside of the unit sphere, the ball around the origin, at an equal distance from the origin. And two documents are near each other if their angle of their vector off the origin is near the angle of the vector of the other off the origin. Now there's an interesting corollary here. Once we normalize each dimension by the vector's Euclidean length, we can compute the cosine of the angle between two vectors by their dot product, which is just the pairwise product of all the entries in the two vectors summed up. So if we have a vector A and we have a vector B, and we have only two entries in each vector, x and y, we can take xa times xb plus ya times yb, and that is the cosine of the angle between them. Now, of course, in a 10,000 dimensional vector, that's 10,000 pairwise multiplications and 9,999 summations. But it's still very simple arithmetic to compute the angle between these guys. That comes from the law of cosines. And here's where it gets really interesting, for normalized vectors, cosine ranking is the same ordering as Euclidean distance ranking. So if you can order documents based on their cosine distance from a query doc, you've also got their Euclidean distance from the query doc. Okay? And so people will speak of cosine similarity as the way to compute how close two documents are together. They don't call it normalized Euclidean similarity, although it is the equivalent thing. And so now we just would seem to need queries that will compute the cosine similarity distance between two documents, and we'll get the ranking we want. But actually, we'd like to do a little bit better than that. And let me talk about what the standard model is next.